lesson, I'm going to be talking about a laboratory technique, a tool that's called Photoelectron Spectroscopy. And what PES, or Photoelectron Spectroscopy, allows you to do is to determine the electron configuration of an atom, of the electrons of an atom. And so what happens is, if you look at this, energy in the form of photons is shot from that machine, and it's shot at an element. And so what happens is, when that energy reaches that atom, if there's enough energy, then an electron or electrons are going to be released by the element and will travel back towards the electron detector. So energy shot at the atom, and if there's enough energy, electrons will be removed and they will travel back towards the detector. So there are three different measurements of energy we have. The first one is the energy of the photon that's being shot at the atom, and that can easily be determined. It's measured by the machine itself. The next energy that you have is how fast do the electrons actually travel back to the detector, and that is measured by the detector itself. So what is its kinetic energy? And it makes sense that if energy is shot at an atom, if an atom's holding on really tightly to its electrons, then the electrons, when they travel back to the electron once they've been released, they're not going to be traveling very quickly. However, if it's really easy to remove those electrons, then they're going, as soon as the energy is shot at the atom, the electrons will move very quickly with a high kinetic energy back towards the detector. And so the term that I've been using, if the electrons are held tightly, if they're not held tightly, this is your ionization energy. And so to determine the ionization energy, what PES does is it takes the difference between the energy of the photon that's shot at the atom and subtracts from it the kinetic energy. Because if the kinetic energy is extremely high, then that means that the ionization energy should be low, because it was easy to remove that electron. If the kinetic energy is low, it makes sense that the ionization energy would be high, because it was difficult to remove the electron, and therefore the electrons didn't travel back with a great speed. So one thing that you can do with this is, if you know the energy of the photon that hits the atom, and you know the ionization energy, you can actually calculate the kinetic energy. You just have to make sure you're in the same units of energy. So we will do that. However, the key benefit of PES, as I had said, was determining the electron configuration of an atom. So let's see how that allows us to do it. So it's measuring the ionization energy of removing specific electrons. So let's look at this. This is a PES, and its purpose is to identify where electrons of a single atom are placed. Okay? So note that the y-axis represents the relative number of electrons, so each peak's height represents how many electrons are going to have a specific ionization energy. Now also note that the closer an electron is to the nucleus, the more energy needed to remove that electron. And so if you notice, at 349, that represents the electrons that are closest to the nucleus, while the 0.42 and the 2.38 are much farther away from the nucleus. And so as a result, we know that the 349 peak, that first peak on the left-hand side, that's going to represent 1s2. Because remember, 1s is the orbital that is closest to the nucleus, so we know that it's going to be 1s2. So the next peak, the 37.1, it is the next closest to the nucleus, therefore it's going to be from the 2s subshell. Now notice, because it's the same height as the 1s subshell, it's going to have 2 electrons. So the electron configuration for that is going to be 2s2. So we've got 1s2, 2s2. Next is going to be 2p. And notice height-wise that peak is about 3 times as large as the first 2 peaks. Therefore, it's going to have 6 electrons in there. So the electron configuration is going to be 2p6. The next sub-level is going to be 3s. Notice it's the same height as the first 2, therefore there are going to be 2 electrons there. The next one is 3p. Notice it's the same height as your 2p, therefore it's going to have 6 electrons there. For the last one, it's going to be 4s, and notice since it's half as tall as the peaks that have 2 electrons, it's going to only have 1 electron. And therefore, this entire PES allows us to determine the electron configuration for this atom. It's going to be